On the left here, we have a solenoid, which is just a coil of wire. And connected to that coil of wire, I have two leads, the red lead here and the black lead in the back here. And that's connected to our oscilloscope up top over here. And on the oscilloscope, you can see we're measuring the voltage. And at the moment, there's no battery across the solenoid, so there's no voltage. So I've just got a flat line right here. But we can see something interesting kind of happens if I just take a magnet. So here's just my regular bar magnet, North Pole, South Pole. And I'm just going to move the magnet into the solenoid coil. And you can see, as I move the magnet up and down, I start to get a voltage. Now there's a couple of important things to note about this. Now if I just hold the magnet here, you can see I get 0 voltage. If I put it inside, you can see I also get 0 voltage. It's only when I'm moving the magnet through the solenoid that we actually get a non-zero voltage. If I pull it out, I get a non-zero voltage. If I push it in, we get a non-zero voltage. Pull it out, push it in. And you can see actually that when I pull it out, the voltage goes up. When I push it in, the voltage gets a dip down. If I flip the magnet around, that's going to be just the opposite. When I pull it out, it goes down. When I push it in, it goes up. And furthermore, we can tell that this is not just due to the fact that I'm putting something in the solenoid. It has to be something with a magnetic field. If I just take a whiteboard marker and I do the same thing, you can see nothing happens to the voltage on my screen. It's only when I take something that's magnetic and I move it up and down, only then will I get some sort of induced voltage in my screen. So what's causing this induced voltage? Now you might ask whether or not the induced voltage is due to the presence of the magnetic material, in this case my little north-south bar magnet, or whether it's due to the magnetic field. Well, we can test that really quick. Here, again, I have a coil that's connected to my oscilloscope over here, and I have next to it, right here, a different coil. This coil is, again, just a solenoid, but I have it connected to a power source. Here's my positive lead coming in, my negative lead going out is on the other side. Right now that power source is turned on so that there is a magnetic field going through the coil. As we mentioned before in our mantra, moving charges create magnetic fields, and then magnetic fields create magnetic forces. Let's see what happens to the voltage in my skinnier solenoid when I pass it through the magnetic field of the big solenoid. You can see we get quite a bit of motion there. My voltage goes up and down. If I move this, as I move this up and down, we can see my voltage increases and decreases. Now, if I were to just turn off the magnetic field from the outer solenoid, so all I've done is turned the power off on the electromagnet that we've created here. If I go in and out now, you can see no motion of the voltage up and down. So it really is the magnetic field that's inducing a voltage in this inner solenoid. The magnetic field from the outer solenoid is inducing a voltage in here. So why is there this induced voltage that shows up? Let's recap. We get induced voltage or EMF, electromotive force, and therefore we would also have some current in these circuits. And we got that when we took a magnet and passed it through a loop of wire. So the interpretation we're going to have for this is that the magnet has some magnetic field. And as we pass that magnetic field, as we increase the amount of magnetic field that passes through this coil, and this magnetic field goes all the way around, as we increase the amount of magnetic field passing through that coil, we get an induced electromotive force that pushes charges around. And it doesn't matter if the magnetic field is coming from a bar magnet or an electromagnet. So here we have some battery. The battery has some electromotive force and voltage. So just like the bar magnet in the first scenario, it too is producing some magnetic field. Again, let's call that magnetic field B. And as I move that coil into and out of the coil that we're inducing the electromotive force in, it's going to create some voltage, it's going to push some charges around in that coil. And again, in both cases, we have this induced electromotive force where the presence of the magnetic field, which is changing, induces some electromotive force. Now that's a particularly important point. In both cases, if I just held the magnet or the electromagnet in place, we would not get any electromotive force. However, when the magnetic field was changing, only then would we get electromotive force that would push the charges around inside the circuit. To summarize, a changing magnetic field B induces an electromotive force through the loop of wire. Now we've got to have a changing magnetic field inside that loop of wire. So we need some way to quantify how much magnetic field, how much B field passes through the loop. And in general, we have a nice quantity that will do that. It'll do it both for magnetic fields, electric fields. This is a general quantity that tells you how much of something is passing through something else. And that's a quantity called flux. To determine how much electromotive force is induced in our coil, we need to compute the magnetic flux. So how much magnetic field is passing through our loop of wire or our solenoid. So we're going to start with a loop of wire, and I need to define some properties of the wire. So the first thing I'm going to do, if I have my loop of wire, I'm going to look at what's a vector that's perpendicular to that loop. Something that's, we used the term normal force before because it was always perpendicular to the surface. This is a line that's perpendicular to the area that's created by this loop. So we've got this, sometimes you write it like this, it's a normal vector. Just means it's perpendicular to the area of the loop. And we have some magnetic field that's passing through that. In fact, we have a bunch of magnetic field lines all passing through that loop. And we want to define the flux as how much magnetic field is passing through this loop. And it's going to depend on the angle that the magnetic field makes with that normal vector. If the angle that it makes is 0 degrees, that means the magnetic field is passing right straight through the loop. If it's passing right straight through the loop, that's going to be more effective than if this angle is not going straight through. So if it's coming through, let's say it's at a 30-degree angle. If I take the extreme version of this, if the magnetic field is moving along the surface of the loop but not actually passing through it, well, that would be a 90-degree angle relative to the surface. It would be moving along the area of the loop, but it wouldn't actually be passing through the loop. So we want to take into account not just the amount of magnetic field, but also, is it actually going through the loop? What direction is it heading? So to do that, we define our quantity in this way. This is our magnetic flux. And it's going to be equal to the magnetic field. So if you have a bigger magnetic field, that's going to give you more magnetic flux. If you have a stronger magnet, you're going to get more induced current or EMF in your circuit. We have our magnetic field. And if I have a bigger area that magnetic field is passing through, we're going to have more magnetic field lines coming through. So it's going to be dependent on the area of the loop. Again, wider loops, you would expect them to have more magnetic field passing through, just because there's more area for the field to pass through. And then lastly, we take the cosine theta. Now, the cosine of the angle will ensure that if theta is 0, I get the maximum amount of flux. Theta is 0 means the magnetic field is passing right through the loop. Cosine of 0 gives you 1. That's the maximum value that cosine can have. In contrast, if the magnetic field is passing along the loop but not straight through it, you're going to have an angle of 90 degrees. The cosine of 90 is 0, which is exactly what we want, because if the magnetic field is not passing through the loop, we want our flux to be 0. So we're going to define our magnetic flux this way. And just by looking at the quantities in here, you can see that magnetic flux is going to have the units Tesla, because it's magnetic field, and magnetic field is measured in Tesla, times meters squared, because we're multiplying by the area. And then cosine theta obviously doesn't have units, so we're just left with units of Tesla meters squared. So we've said you need a changing magnetic flux in order to induce an electromotive force in a coil. So there's 3 ways to change magnetic flux, and we can tell just by looking at the equation that the 3 ways are going to be changing the magnetic field, the area, and the angle that the magnetic field makes with the loop. Okay? Changing magnetic field is simple enough. All you have to do is take your magnet, and if the magnet is far away, and you bring it close to the loop, all of a sudden we'll have magnetic flux going through the loop, whereas originally the magnet was too far away and then you had very little magnetic flux going through the loop. So I could take the magnet from far away and bring it close. That would create a changing magnetic flux. I could also do the reverse. Here, you have magnetic flux going through the loop. If I pull the magnet away, I have less magnetic flux going through the loop. So again, our magnetic flux has changed. Nature doesn't say that you have to increase the magnetic flux. All it says is that the magnetic flux has to change. And one way to do that is to change the magnetic field by bringing the magnet either further or closer to the loop of coil that you're interested in. The next method of creating a changing magnetic flux is to change the area of the loop. Now you might think, how do you change the area of a loop if the loop is some metal wire? Well, we could bend and deform the wire. That's one way to do it. Another way to do it is, let's suppose we start off with a piece of metal that's in the shape of a U. And what we're going to do, we're going to create some magnetic field. X's that I'm drawing just means that there's magnetic field into the page. So some magnetic field pointing into the page, or in my case, into the board. In your notes, it should be into the page, unless you're chiseling something into granite or writing on a chalkboard. However you take notes, I'm not too particular. But we don't have a complete loop here. How do I get a loop? Well, suppose I just make a piece of metal, and I drill 2 holes into it, and then I slide that piece of metal onto my U-shaped bar. So we have here just a little slider. And the slider can move back and forth. All I'm doing is I'm grabbing the slider and moving it back and forth, and then sliding the U-shaped metal through the holes in the slider. And if my magnetic field is uniform across that slider, then what's going to happen, as I slide my slider to the right, all of a sudden I have more area. More area means we're going to have more magnetic field passing through my loop. And we can tell because we've got more magnetic field lines passing through the loop. Okay? So again, I can increase my area by pulling the slider bar to the right. I can decrease the area by pulling the slider bar to the left. All we're doing, again, is just sliding a piece of metal back and forth across a U-shaped piece of metal. And that increases the amount of magnetic field that passes through the loop because I have a conducting loop here once I put that slider on. So the second way that we can create a changing magnetic flux. Again, magnetic flux is just telling you how much magnetic field passes through the loop. If I make a bigger loop, I get more magnetic field passing through the loop. The third thing we can do to create a change in magnetic flux is change the angle at which the magnetic field penetrates the loop. So here I have a square loop. We're viewing it at an angle here. I've got a magnet, and most of the magnetic field is coming through at a right angle. However, all I have to do is move my magnet, just rotate my magnet ever so slightly. Now the magnetic field, instead of coming straight through, is now coming through at some angle theta. So as before, I can either go from coming straight through to coming through at an angle, in which case I get a change in the magnetic flux. Since the angle changes, the magnetic flux is going to change. We also get a change in the magnetic flux if we start at an angle theta and then rotate so that the theta becomes 0 degrees. Again, both cases will change the flux. It doesn't matter whether you're increasing or decreasing the flux. A change in the flux is going to create an induced electromotive force in the loop of wire. How can we tell which way an induced current is going to go? If we have a loop of wire, then the current could go clockwise or it could go counterclockwise. Well, to determine which way the current is actually going to go, which way the induced current is going to travel, we use something called Lenz's Law. Lenz's Law goes as follows. It gives the direction of the induced current, and what it says is that nature abhors a change in flux. And I underline the word abhors because I love that word. First time I saw this in a physics class, I just loved it. Abhors. Abhors means really, really hates, like despises. Despises a change in flux. And in fact, the induced current I I should go back. What happens is that you induce a current I that opposes a change in flux. Nature abhors a change in flux, and it's going to induce a current in the loop that's going to try to cancel out the change in flux, or at least slow it down. It doesn't cancel it out completely. It's going to try to cancel out that change in flux. Let's see how that works. Suppose we have a loop of wire drawn here in white, and we have some magnetic field going into the board, represented by these green X's over here. Now, let's consider the case that B increases. And if the magnetic field B increases, that means the magnetic flux is also going to increase. And nature abhors that. It does not want the magnetic flux to increase. So it's going to try to prevent it as much as possible. So over here, we have a picture where we have an increased magnetic field. Notice there are more field lines. There are 4 field lines here. There are only 2 over here. Nature doesn't want that to happen. So nature wants to cancel out some of that field. To do that, let's see, what's a good color? I'll use yellow. Nature is going to try to create a magnetic field in the opposite direction. How can it do that? Well, it can do that by inducing a current. And remember, a current is a set of moving charges. Those moving charges will create a magnetic field. Is the current going to go counterclockwise around the loop, or is it going to go clockwise around the loop? Well, it's going to go in the direction that creates a magnetic field that's going to try to cancel out these magnetic field lines going into the board. So we're going to create some induced magnetic field coming out of the pig. Remember, induced magnetic field, magnetic field coming out of the page, or any vector coming out of the page or out of the board is just represented by a circle with a dot going through it. So this is going to be some induced magnetic field coming out of the board. The change in magnetic field goes into the board. The induced magnetic field goes out to oppose that. And that magnetic field arises because there's some induced current. And the induced current has to go counterclockwise in this case. Why counterclockwise? Well, if I use my right-hand rule, I can figure out that the induced current creates an induced magnetic field that points out. So we have magnetic field pointing in. That magnetic field increases, which means magnetic flux increases. Nature doesn't like that. It wants to cancel out some of that flux increase, and it does so by by inducing a current in the circuit that goes counterclockwise. The counterclockwise current creates a magnetic field given by the direction of my thumb, whose direction is given by my thumb, pointing out of the board, to cancel out the magnetic field that goes into the board, so that we get an induced magnetic field that opposes the change in the flux. Okay. Again, it just goes back to Lenz's law. Lenz's law says nature abhors a change in flux, and it's going to induce a current in such a way to oppose that change in flux. Well, we can do that by making a current that goes counterclockwise. Suppose we consider the opposite case. I start with a bunch of magnetic field. Got 4 magnetic field lines passing through my loop. I decrease the magnetic field. Magnetic field through the loop goes down, which means the magnetic flux is going to decrease. Nature doesn't like that. Nature doesn't like changes in flux. It doesn't mind flux. Flux is fine. But whenever the flux changes, nature has a problem with that. So nature, it will turn out, wants to oppose this change of flux. And to oppose it, it's going to try to create more flux. If the flux goes down, nature wants to increase it to prevent the change. So you get induced magnetic field into the board. Why is it into the board? Well, it's into the board because we've lost some magnetic flux that was going into the board, so nature's going to try to compensate. Well, how does it create that flux? Again, it's going to do that by inducing a current that can create magnetic flux into the board. And to get flux into the board, we would have to have a current, an induced current. Induced current that goes clockwise. You can see if it's going clockwise, my induced magnetic field has to go into the board. No matter how you do the right-hand rule, as long as you're doing it correctly, you can show that the current has to be clockwise to get that magnetic field into the board. So to recap, we have magnetic flux shown in green, the green axis here. It's decreasing, or magnetic field shown in green. Magnetic field is decreasing, which means our flux is decreasing. Nature abhors any change in flux. Doesn't mind the flux, but it minds the change in the flux. So nature's going to try to create magnetic fields to cancel out the magnetic field, or to compensate for the magnetic field that we've lost since it's gone down. And to do that, it creates this induced current. The induced current goes in such a way that it'll create a magnetic field that'll compensate for some of the magnetic field we've lost. Again, it all just boils down to nature abhors a change in flux, so that if you have magnetic flux pointing into the board and the flux decreases, nature's going to try to create more flux to build that back up.